Hello everyone, welcome to the course Data Structures. This is Thulasi Chitra, Associate Professor, Department of CSIT, MLR Institute of Technology. In today's session, we will be discussing about Bellman-Ford algorithm. Under this, we will be discussing about what is Bellman-Ford algorithm, introduction, then example on Bellman-Ford algorithm, and what are the drawbacks we are going to find with Bellman-Ford algorithm. These three concepts we are going to discuss under this Bellman-Ford algorithm. As we know that this is one of the shortest path algorithm. Now, what is this Bellman-Ford algorithm is? It is a single source shortest path algorithm. This algorithm is used to find the shortest distance from the single vertex to the all other vertices of weighted graph. The same thing we have applied in our Dijkstra algorithm also. In Dijkstra's algorithm also, we have done the same. We are going to take a single source. From that, we are going to find the shortest distance from that single vertex to all other vertices based on the weighted graph. But here, what is the disadvantage we find with Dijkstra's algorithm? That one also we will see in the next point. Okay, there are various other algorithms used to find the shortest path like Dijkstra's algorithm, etc. But if the weighted graph contains the negative weight values, right? In a graph, if we are going to have the negative weight values, then Dijkstra's algorithm does not confirm whether it produces the correct answer or not. If you are going to have the negative weights in the graph, that may not, that is the Dijkstra's algorithm will not produce the correct answer. So for that, what we are going to do, we are going to move to this Bellman-Ford algorithm. In contrast to this Dijkstra's algorithm, Bellman-Ford algorithm guarantees the correct answer even if the weight graphs contains the negative weights also. If in a graph, if we have the negative weights, then we can go ahead with the Bellman-Ford algorithm. That may give you the correct result. Okay, let us see. Consider the below graph. This is the graph that was given. If you can look here, here we have the positive weights. These are nothing but the weights of a graph, right? Here we have some positive weights over there, some negative weights also there, right? Now, as we observe in the above graph, some of the weights are negative. So that the above graph contains 6 vertices. So, we will go on relaxing till up to the 5 vertices, right? Among these, how many vertices we have? 1, 2, 3, 4, 5 and 6. Totally 6 vertices are there. But we are going to do this iterations based on 5 iterations only. The rule for this algorithm, we are going on relaxing all the edges n-1 times where n equal to number of vertices. Here we have 6 vertices, that means we are going to relax it for 5 times. And here we will relax all the edges 5 times. The loop will iterate 5 times to get the correct answer. That means the same thing will be repeated. The same loop will be repeated for 5 times to get the correct answer for each and every vertex. If the loop is iterated more than 5 times, then the answer will be the same. If the loop is repeating for 5 times after second iteration also, if we have the same values, if it is iterating for another 3 times also, we will be having the same answer, right? There would be no change in the distance between all the vertices. After doing so many number of iterations also, there will you don't find the difference between the vertices, right? You'll be having the same values for all the vertices. That is the meaning of this one. Now, relaxing means what? How we are going to relax? The same thing we are going to apply in our Dijkstra algorithm also. If d of u plus cost of u comma v is less than d of v, then how we are going to find d of v? D of v equal to d of u plus cost of u comma v. Cost is nothing but you can say it as weight of u comma v. U to v. What is the weight you have? But here for Bellman food algorithm, here we are going to find what is the first step we need to do is we need to find or we need to write down all the edges which was given in the graph. Okay, we need to note down all the edges which are given in the graph below. Now observe here, these are the nodes where we have, and what are the edges we have? We have A to C, A to B is one edge, A to C is another edge, and A to D is another edge. The edge is nothing but from that particular source node to the destination node, how it is moving. That is outgoing edge from source node to the destination edge. That is nothing but an edge how we are going to write. That is A to B, A to C and A to D. These three nodes. And B to E, this is one more. And C to E is one more. And D to C you have one edge. And D to F also you have an edge. And E to F we have an edge. And we have C to B also we have an edge. These are all the edges first we need to make note of. Right, for Bellman food. Now, after noting all this, now observe the graph how it is represented. For after representing all these things, now we need to represent the source vertex with 0 value and the remaining vertices with all infinity. That means we need to represent infinity for all the vertices. Initially, the distance of all the vertices are infinity other than the source vertex. Now, we are going to follow the first iteration. Consider AB. That means we are going to consider this particular edge. Right? After considering this particular edge, now we need to consider A as U and B as V. Okay? Now, find the relaxation for this. U value is 0 and V value is infinity. Now, cost of u comma v is nothing but this one. Cost of u comma v is nothing but 6. Now, how we are going to find d of v? This one we need to find it out. Now, d of v equal to d of u is nothing but 0 plus this cost of this one is 6. So, we are going to get the value as 6. Now, what is the distance of vertex v? Vertex v is going to be replaced with 6. Now, you can observe here what is the value you are going to get. I am going to get the value as 6. In the similar way, I need to find the distance for C, A to C. Now, this is U and this is V. Now, apply the same relaxation formula. D of V equal to D of U plus D of that is cost of u comma v. That means you are going to get 0 plus cost of u comma v is nothing but 4. You are going to get the value as 4 for A to C, right? For C, you are going to get the value as 4. Okay. In this way, we are going to have. Next, I am going to find the distance for A to D. Now, how I am going to find? This is 0, 0 plus 5, nothing but you are going to get the value as 5. Previously, it was infinity for all these values B, C, D. Now, it is 5. Right? Now, after this is for the 3 edges we have find it out. Next, we are going to find it for B to E. B to E. What is the cost of, what is the U value of B? B is nothing but 6 plus cost of U comma V is nothing but minus 1. That is this one. Right? So, we are going to get the value as 5. Now, instead of infinity, we are going to replace that with 5. Okay. Next, we have the next edge is C to E. C to E, you have the cost of the vertex of C value is 4. 4 plus the cost of C to E is nothing but 3. That is nothing but 7. Okay. But when you can see 7, already we have the minimum value 5. That's why we are not replacing with 7. 5, we are going to take only the minimum value. That's why we are going to place 5 as it is. We are not replacing with 7. Minimum value is 5 only. Okay. Next, coming to the next one, we have D to C. D to C. Now, D value we have 5 minus 2. 5 minus 2 is nothing but 3. Now, Here for the C vertex, already we have the value as 4. But whatever the new value we got, it is 3. So we need to replace 4 with 3. Right? Which is the minimum value we are going to get, that has to be replaced there. Right? Now, so C is now 3 value. Next, if I am going to see D to F, what is the D to F value? D to F value, how I am going to find D value? U value is 5. 5 minus 1 is nothing but 4. Right? Still, I don't have the value of for F. F is infinity only. So, 4 is less than infinity. So, I am going to replace with 4. Like this. Now, what is the next vertex we need to consider, or edge we need to consider? E to F. This one. E to F. For that, E value is 5 plus 3. 3 is nothing but 8. But I have the value for F is 4. But 8 is greater than 4. So, I am going to consider 4 as the minimum value. I am not going to change the value for F. F is having only the 4 value. Right. Next, we are going to consider the next edge is C to B. This one. C to B. This part. But C is having 3 and the cost of C to B is minus 2. So, we are going to get the value as 1. When I am doing this, I need to replace. Already we have the value for vertex B is 6, but it is greater than 1. But the minimum value for this is 1. So, we need to replace that with 1. Okay. Like this way, we need to find the distance of every vertex values. After finding all the vertex values, this is the graph where you are going to get it. Okay. After first iteration, these are the values, updated values for each and every vertex. Now, I am going for the second iteration. Right. I have done it for all the vertices. Now, going for the second iteration, the same procedure we are going to follow. Now, A to B. Check for A to B. 0 plus 6 is nothing but 6. 6 is not less than 1. So, I am going to place 1 as it is. And A to D. Sorry, A to C. For A to C, 0 plus 4 is nothing but 0 plus 4 is nothing but 4. 4 is not less than 3. So, I am not going to replace with 4. 3 will be as it is. Next, A to D. A to D we have 0 plus 5 is nothing but 5. But already we have the 5 value. So, no change in that. Okay. Next, we have B to E. For B to E, you have actually the B value is 1. 1 minus 1, that is nothing but 0. Right? 1 minus 1 is nothing but 0. Now, I need to replace E with 0. Because 0 is less than 5 value. So, I need to replace 5 with 0. This is the only change we find. Next, if I am going to check for C to E. C to E, what is the value? C value is 3. 3 plus 3 is nothing but 6. 6 is greater than 0 because we are not going to replace 0 with 6. 0 is the minimum value. Next, I am going to check with the D to C. What is the D to C value? 5 minus 2 is nothing but 3. There is no change. So, we are going to place a C vertex with a 3 only. Next, D to F. D to F, you have 5 minus 1, 4 only, no change. Next, we have E to F. E to F, we have 0 plus 3. So, we are going to replace 4 with 3. Why? Because already we have 4. 4 is greater than the 3 value. The minimum value is 3. So, I am going to replace with this 3. Next, we have the last one, C to B. C to B, you have 3 minus 2, that is 1. There is no change. This is the finalized distance between the vertices where you got. That is for A it is 0, for B it is 1, for C it is 3, and for D it is 5, and for E it is 0, and for F it is 3. Right? Like this way we have find out for the second iteration. After second iteration, these are the values where we got it. Now, if I am going to check for the third iteration also, I don't find much more. I don't find any changes in the vertices of each and every edge. If you want to check, you can check the third iteration, fourth iteration, and fifth iteration. After doing all the 5 iterations also, you will be getting the values of A is 0, B is 1, C is 3, D is 5, and E is 0, and F is 3. You don't find any changes in these vertices. If you want, you can check with third, fourth, and fifth, the same procedure what we have followed based on the relaxation. Okay. This is about the Bellman-Ford algorithm, and we have one disadvantage with the Bellman-Ford algorithm. What is that? Here, the Bellman-Ford algorithm does not produce a correct answer if the sum of edges of a cycle is negative. If the sum of edges of cycle, if I am going to, it is going to form a cycle in that particular case. If I am going to have like this, if I am going to have a graph like this, if it forms a cycle, right, it is forming a cycle here. Because of this, sum of edges of cycle is negative, then it is not going to give you the correct answer. Okay, let us understand this property, how this works, how this is going to, how the disadvantage is going to be shown here, right? This is a graph where it is going to have one negative edge, and we consider vertex 1 as a source vertex and provides 0 value to it, and we provide infinity for all the vertices. Yes, as you know, the same procedure we have followed. We have placing source vertex as 0 and the remaining all vertices with infinity. And after that, what we need to do, we need to write all the edges for it. That is 1 to 3 is one edge, and 1 to 4 is 1 to 2 is another edge, and 2 to 4 is another edge, and 3 to 2 is another edge, and 4 to 3 is another edge. These are all the edges we have written. Now start our first iteration. This is my first iteration. I am going to consider 1 to 3. We know the relaxation formula. Based on that, we are going to do 0 plus 5. 0 plus 5 is nothing but 5. So I am going to replace this with 5. I am going to replace infinity with 5. Next, consider 1 to 2. This one I am going to consider 1 to 2, 0 plus 4. 4 is less than infinity. So I am going to replace infinity with 4. Right? Done. Next, I am going to consider 3 to 2. 3 to 2 is this edge. 5 plus 7 is nothing but 12. But here for this vertex 2, I have the minimum value. 12 is greater than 4. I am not going to replace with the 12. It will be having the minimum value 4 only. Next, I am going to check for the next condition 2 to 4. 2 to 4, we have 7 plus 4 is 11. But here we have the infinity is greater than 11. So I am going to replace infinity with 11. Okay. Next, from 4 to 3. From 4 to 3, what is the value? We have 11. 11 minus 15, we have minus 4. Right? 11 minus 15 is minus 4. So, 5 is greater than minus 4. So, I need to replace that with minus 4. Like this way, we are going to do. Right? This is after the first iteration. These are the values where we got. Now, this is the after first iteration. These are the values where we got. Now, apply the second iteration. Now, again check for 1 to 3. 1 to 3, 0 plus 5. 5 is greater than minus 4. So, I am not going to replace anything with this. Next, 1 to 2. What is the value? We have 0 plus 4. 4 only. No change. Next, 3 to 2. 3 to 2, you have minus 4 and plus 7. Minus 4 plus 7, you are going to get the value as 3. So, I need to replace, instead of 4, I need to replace that with 3. Right? I am replacing with 3. Next, we have 2 to 4. 2 to 4, here we have change, means automatically here also it will be changed. Here actually we have 7 plus 3, you have to get 10. Yes, previously it was 11 actually, but that is replaced with 10. Next, we have 4 to 3. 4 to 3, you have 10 minus 15. 10 minus 15 is minus nothing but minus 5. Minus 5 is lesser than minus 4. So, I need to replace minus 4 with minus 5. Okay. After second iteration, these are the values where I am going to get it. Okay. Now, come to the third iteration. This is my second iteration values. Now, come for the third iteration. 1 to 2. 1 to 2, 0 plus 5. 5. 5 is not less than minus 5. So, we are going to place as it is minus 5 itself. Next, 1 to 3 is that one. 1 to 2. 1 to 2, we have 0 plus 4. 4 is greater than 3. So, I am going to place 3 as it is. 3 to 2. We have 3 to 2. 3 to 2 is nothing but minus 7 plus 5. Minus 7 plus 5 is nothing but 2. So, I need to replace this 3 with 2. So, I need to replace this 3 with the 2 value. 2 is the minimum value, right? Next, I am going to have 2 to 4. 2 to 4, 2 plus 7 is nothing but 9. So, I am going to replace 10 with 9. Next, the other condition, we have 4 to 3. 4 to 3, you have 9 minus 15 is nothing but minus 6. So, we need to replace minus 5 with minus 6. These are the changes after the third iteration. This is the final graph where I am going to get it after the third iteration. And after the third iteration, we got this is the final values for each and every vertex. Now, if you could observe, since the graph has 4 vertices, how many iterations we need to do? We need to do only 3 iterations. But what is happening here? There would be, so according to the Bellman-Ford algorithm, there would be only 3 iterations. If you try to perform 4th iteration on the graph, the distance of the vertices from the vertex should not change. If I am going to perform one more iteration, the values of these vertices should not change. But what is happening here? But here, if the distance varies, it means that Bellman-Ford algorithm is not providing the correct answer. If I am going for the 4th iteration, again the values are going to be changed here. Because of that, this is not producing the correct result. In the 4th iteration, if you could observe, 1, 3, you don't find much, for 1, 3, what is that 1, 3? 1, 3, 0 plus 5, you don't find change. But 1, 4, 0 plus 4, you don't find change. But for 3, 2, 7 minus 6, again this value is going to be changed to 1. 7 minus 6 is 1. Now this one, 2 to 4, 2 to 4, 1 plus 7 is nothing but 8. But this one, 8 minus 15 is nothing but minus 7. So, I need to replace all these values. After third iteration, there should not be any change. That will give you the correct answer in the Bellman-Ford algorithm. But here in the 4th iteration also, the values are changing. Because of this, it is not producing the correct answer. Right? Now, when you see about this Bellman-Ford algorithm, we have already discussed about what are the different shortest path algorithms, and under Bellman-Ford algorithm, we have discussed what is Bellman-Ford algorithm and what is the relaxation part of it, and what is a drawback that overcome here with Dijkstra's algorithm also. And we have seen the example of Bellman-Ford algorithm, and we have seen what is the drawback with the Bellman-Ford algorithm. I hope you understand this concept. Thank you.